What's up, everyone? It's Calc time with Miss Wesley. Very excited to be here. We've been working with definite integrals. We've been working with a combo of geometry and calculus to get area under a curve. And today's time, we get a little bit more practice with some good ones in your definite integrals packet on page 17. So join me there. Get excited. Get ready to take some notes. As you're pulling your packet out, I thought what could be better to entertain you than a couple jokes. The first one is, what do you call it when a strawberry gets hit while crossing the road? You'd call it traffic jam. And the second joke is mountains. I just wanted to talk about mountains. Mountains, they're not just funny. Some may say that mountains are hill areas. Like hilarious, hill areas. I thought that was a good one. Looking at the top of page 17, the first question's good as a warm-up. It says, do what we've been doing lately. Find the area of the region under this curve, this quartic function, f of x. And then they give us limits of integration too. They set that up for us. So really, I want to talk about a picture of this function because I think it would be good to visualize it. But we can set up this integral if we want to, even without a picture. I'll call it A for area. We want to integrate from what? This x value to that one? So from -3 to 0. What do we want to integrate? We want to integrate this function. This is what's going to bound the region from the top. So 2x plus 6 to the fourth power. And do it with respect to x. Think of what you know 2x plus 6 to the fourth to look like, and you can confirm this with a calculator. One thing that's going to be helpful on some of these future questions is to get x-intercepts of these functions. And I know this one's to the fourth power. Its end behavior is going to be up and up, just like any even function would behave. You can get the x-intercepts, and I think there's just one of them here, by setting the function equal to 0, solving 0 equals 2x plus 6 to the fourth. The only thing you'll get to make this 0 is just setting the inside equal to 0, which should give you -3 for x. And a calculator or Desmos would confirm this. This thing's going to hit the x-axis and bounce off of it at x equals -3. And the area we want, because I know it's good to visualize this too, I'm going to shade this in red. We just want the area from -3 over to the origin, over to 0. This shaded region here. That's what we're looking for. So this would be a good one, and especially at different parts during the video, if things seem to be going quickly, feel free to slow me down, pause me, rewind me, or try a problem on your own while pausing the video and then go back to check your work. For this one, it's looking like your classic composite function where you have this inside part of the function, that outside part, the main event, the fourth power. You can either guess this integral, which is possible, it's not too bad, or this might be a good time to pause and just review u sub if we haven't used it in a little while. Lots of times we have some success when we call u the innermost part of the expression, so just the 2x plus 6 without the fourth power. And then you'll recall we go through, right, we take our derivative, du dx, which would just be 2 here, and we can use, we can multiply both sides by dx to get dx by itself. So we'll say du equals 2 dx, and then divide both sides by 2. So an expression we can use for dx would be du over 2. Okay, so just refreshing u substitution. Both of those circled expressions can get plugged back into the original integral. So we've got, and remembering, now we're kind of changing our variables here. We're going to write u to the fourth instead of 2x plus 6 to the fourth. And then instead of dx, what are we writing? This fraction, du over 2. But just remember, just keep in mind, these are both x values. I might even write x equals -3 to x equals 0 just to remind myself I can't plug in -3 and 0 too early while I still have u in the problem. I want to wait until the end when it's all in terms of x. So next step would be to integrate, right? Feel free to try it on your own. You've got a constant 1/2 that'll stay in that integral. We need to integrate u to the fourth power, so we'll bring it up to the fifth power and divide by 5. Okay. And then we're evaluating it between two different x values, from x equals -3 to x equals 0. Okay, so now might be a good time to get this problem back in terms of x, so we can do that plug-in. So we have the fraction 1/10. We've got, what is u? 2x plus 6. So 2x plus 6 plug back into the fifth power, and then evaluate it from -3 to 0. Last part's the plug-in. In the video, I'll kind of zip through this part. You want to take this a little bit slower and be more careful with it so as not to make a mistake. But we're plugging in 0. We're subtracting what we get when we plug in 3. So it still is 1/10. With 0 plugged in, you'll just have 0 plus 6. So it's 6 to the fifth. and then minus what we get when we plug in -3. So -3 plugged in, I believe, gives you all 0 here. -6 plus 6. I think it should be -0 to the 5th. This answer will be 6 to the 5th power, a huge number divided by 10. I think I left it like that as a final answer. When typing it into the calculator, you get something up in the 700s. 777, rounded to the nearest tenth, 0.6 square units of area. Okay, so then I want to kind of skip around this page and the next page. Number 2, I like the looks of this one because I feel like for this one I would not need a calculator to sketch this graph. I got to think back to what I know about the curve y equals square root of x because we want to kind of shade a region underneath of it. So y equals square root of x, I call it a french fry because I don't have a better name for it. Usually when I'm graphing it, I think of easy values to square root. Like 0 is easy to square root, right? The square root of 0 is itself. Square root of 1 is 1. You have a point there. Square root of 4 is 2. And then just enough room, 5, 6, 7, 8, 9 is a perfect square. And square root of that's going to be up at 3. So you get this red curve. And we want to conveniently evaluate it between these two perfect squares. We want to evaluate it between the lines x equals 4 and x equals 9. So again, not a bad idea to get a sense of what this shaded region looks like. I mean, the last one was a huge amount of area, almost 800 square units, because that graph rose so quickly. In this one, not so much. I mean, it'll be good to be able to get an answer and then maybe just check it to make sure it makes sense based off of this picture. So could we still set up the integral? You've got area. I'll call it A for area again. And you're evaluating area between these two x values. So this is another problem where we get kind of lucky. They give us the limits of integration. We don't have to find them on our own. And we'll go from 4 to 9 of the square root of x. No fancy tricks or u substitution needed here. We're just going to evaluate the integral of x to the 1/2 power dx. So again, if you feel like pausing, trying this problem on your own, and then checking back in to see the answer, that's great. I want to integrate x to the 1/2. I want to bring that up a power. So we've seen this before many times. This should be x to the 3/2 divided by 3/2, evaluated from 4 to 9. And while I'm on the mode of not using a calculator too much, let's see if we can refresh our exponent rules and evaluate as much of this as we can without it. You've got the 2/3, the constant out front. We need top number minus bottom number. So 9 to the 3/2 plugged in minus 4 to the 3/2, right? And we know a 3/2 power. It's going to square root the base, and then it's going to cube that square root. So you square root of 9, you get 3, and then cube that to get 27 should be our first expression. Same thing with the 4. Square root of 4 gives you 2, and cube that to get 8. So this answer simplified could be 2/3, we could just say, of 19, which is also known as 38/3. And that looks pretty good. I want to skip down to the, actually to the next page. The next 2 problems would be pretty good for you to try on your own for practice. If I just skip over to page 18 here, there's a really good one at the top. And this may be the first time together that we've been asked not just to find area between a curve and the x-axis, but number 5 at the top of the next page asks you to find the area of a region in between two curves, just enclosed between them. I believe what we already know about definite integrals can help us get through this too, and I do think a picture would help us get on the same page for starters. So it says sketch a graph and shade the area. So here goes y equals x squared. We'll sketch just, seems like the quadrant 1 portion of this parabola. Dot at 0, 0, 1, 1. Maybe we'll show 2, 4. This is the right side of that parabola. If we need the left side, we could show that too. But for now, I'll just focus on the right. It'll come up this way as well. And I'll label it y equals x squared in red. And then maybe in blue, let's graph y equals 2x. So 2x goes through the origin, and it has a slope of 2, this straight line here. So this time, we don't need, like I said, we don't need area down to the x-axis. This is y equals 2x. We want area enclosed between two curves. So just shaded in green, it's this little sliver, kind of like a crescent shape in between those two curves. Now I wonder, area between two curves. So we have a function kind of in blue that bounds the region from the top, and we have a function in red that bounds the region from the bottom. I wonder, could we just, if we're going, it looks like the integral runs between two x values from 0 to 2. couldn't we just take the integral, and I'll say for this, let's say we're just going from A to B. I wonder if, we'll write this down as our setup, we could take the integral of the top function, I'll say FCN for function, minus the bottom function. And let's talk about why that would possibly make sense. So bottom FCN for function, taken with respect to x. Let's think about it. If we just integrated the blue function, hope I don't clutter up this picture too much, but I should get all the area here in yellow. This would be blue down to the x-axis, would give me all the yellow area. Well, if I subtracted the integral between the bottom function and the x-axis, the leftover should be what we need. If I subtracted maybe this region in pink, I don't know if I've cluttered this up too much, but what's left over should be the region that's in green. And this method will always work as long as you can decide which function bounds the region from the top and which function bounds the region from the bottom. And we'll get more into practice with this over the coming days. So for this one, let's do the setup here. The area we want goes between, it looks like, these two convenient x values. So where these two graphs intersect at 0 and 2. What's bounding the region from the top? So that's the blue line. That's 2x. We want to subtract the area between the curve and the x-axis. So we want to subtract, what is it? Bottom function would just be x squared. And now we've got our integral set up, right? The next part should be easy. I don't see any u sub required again, and we can integrate and do the plug-in. So we'll just do it. Again, feel free to pause and then come back and check your answer. So we've got an integral here, 2x. So integral of 2x should just be x squared, right? 2 over 2 would go with it. And then minus, how about we bring this up a power, x to the third over 3, and we'll evaluate it from 0 to 2. So that means definite integral, we plug in 2 first. We'll have 2 squared, so 4, minus 2 to the third over 3, so minus 8 thirds. And we want to subtract just 0 minus 0. So for this one, really just 4 minus 8 thirds. That's kind of like saying 12 thirds, take away 8 thirds, leaves you with 4 thirds of a square unit. And that should be it for that one. So the first time doing region between two curves. Lastly, I want to look at number 6. It's got a little bit of trig in it, right? It says sketch a graph, shade the area of the regions bounded by y equals sine of x and the x-axis over the interval from negative pi to pi. Ooh, okay, so we got to think back to what sine looks like. So the sine curve is going to intersect the x-axis at an infinite amount of spots, right? Sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is also 0, if I think back to what this sine curve looks like. Sine's going to rise up to 1, the highest it ever gets to, and fall to -1, right? So this would show up on a calculator as well. This would be the region between 0 and 2 pi. Now what we need to focus on here is the region between negative pi and pi. So can I extend this to the left a little bit? It's also, right, this should repeat to the other side. 2 pi should have some zeros here, and this thing goes down and then up. So rough sketch, but the region we care about just is this portion and this portion. A very symmetric graph as well. I noticed this problem in all caps says to find the total area, and I wonder why that's a really good idea. Let's think. Well, we know that in calculus, area below the x-axis always counts as negative, and area above the x-axis counts as positive. And to me, this looks like a beautiful symmetric sine curve where the net area should just be 0 here, right? The area down here should cancel out the area that's above the x-axis. So that's not what we want. It says don't just take the integral from negative pi to pi of sine of x, because you'd just be getting 0. What we really want, the way we should write it, is we want the integral of the absolute value. If all this area, this total area, were considered positive, what would it add up to be? One of your easiest ways to do this, you might guess, would just be, why don't we just find this area here, just from 0 to pi of sine of x dx, and then what? Maybe we double it, right? So that we can add up the areas of the two regions. I'm going to leave this to you. I guess our next step would be to integrate, right? So we could write that part. The integral of sine is negative cosine, so you'd have -2 cosine of x. And then you're going to do the work and plug in 0 and pi and use your exact values to evaluate that definite integral. You should get something positive for your answer. Okay, I'll leave you there. Don't have too much fun. Have a great day.